Today it is power and efficiency. Please take that down. Power and efficiency. So the last time we discussed energy, work and energy, right? So then write the subtopic power. Power, take it down. So what is power? Power is rate of work done. We can say that power is rate of work done. So we know work is just force times displacement to the same side. So if we divide that by time, we get the power, right? Then just under this write rate of work done. Rate of work done. Then we can have this equation. So whenever we need to make a rate, you just have to divide it by time. So this is work done divided by time. So meaning W over T, right? So that is the power, work divided by time. Take this down as I'm going through. So according to this one, what is the unit of power? This also is important. Unit of power. So work is measured in joules. This is seconds. So this should be joules per second, right? Joules divided by second. So that is joules per second. We can give this a single unit as watt. So 1 joules per second is equal to 1 watt. Okay. Then we need the dimensions of power. So you should be able to find this. So we know that power is work divided by time. So what is the work? Work is Fs divided by time. So the dimensions of force is mLT minus 2. This is L. This is displacement. So that is a length divided by time. So we get dimensions of power as mL squared T minus 2, T minus 3 actually. This gets squared. This goes up minus 1, minus 2, minus 3. So this gains as mL squared T minus 3. So that's the dimensions of power. And this is the units of power. So power is measured in watts, right? Not joules. Power is measured in watts. First, take it down. Take this down. Right. So now we have a basic understanding of power, right? That is rate of work done. The thing is, there are other forms that you can write power, right? Actually, you know, when work is done on something, that system gains energy. So the work done is equal to the energy gained of a system. So instead of work done, this is the another form for that equation. Power can be written as, instead of work done, I can write energy gained. Then divide by time, right? So that this equation also can be used to find the power, right? Take it down. Then we have another form, one more form. Let's say you make a force on this object and it moves a distance s to here. There can be other forces on this object. Due to this force, the object moves from here to here. There can be other forces also, right? If this happens within a simple t time period, if this happens within a simple t, then you can find the power of this force. Usually this force is what we call driving force. Driving force. Okay. There can be resistive forces any number of forces on this. But this power usually is provided by, let's say, a car or something. Usually it is provided by the engine of a car, if it is an engine. Okay, so we call this driving force, and move distance is s and the time is t. So if you need to calculate power at this case, you can see it is work divided by time. So work is equal to force times displacement divided by time. So displacement divided by time, we can do it as velocity. Then we have this equation for power, F times V. So F is what? F is the driving force, right? V is the velocity at a moment. So you can have this form. There are many questions you need to do using this equation as well, right? So those are the three main types of equations that you will need to use whenever you are solving problems, right? Okay, take everything down. Right, so before moving on to efficiency theory parts, we'll discuss a few questions on power, right? Right. First essay question. There's essay question. Try that essay question. Give you a minute. And if you are seeing the recording, please pause. First try the question, right? Right. So the first question, heater generates a heat quantity of 25 kilojoules within 20 seconds. Find its power. You just have to apply this equation. P equals, here actually it is energy gained, right, divided by time. So the energy gained is just 25 kilojoules divided by time. So the time is 20 seconds, right? So if you divide 20, this becomes 2.5 divided by 2, so it is 1.25. Kilo remains as same, joules per second, which is watts. Okay, so this is the power of the heater. That is the rate of energy generated by the heater, that is 1.25 kilowatts. So that's the first question, right? So those are easy questions. Okay, right, then try a second question. Try that. I'll give you a minute. Try that second essay question. Okay, so here the power is 1.5 kilowatts. 1.5 kilowatts. Okay, then the heat provided, that is like energy gained, right? Energy gained is 48 kilojoules. Here what they ask is time. This is what they ask. Okay, so kilo cancels off. Take time to this side. So 48 joules divided by 1.5. 1.5 means 3 over 2. Okay, 3 over 2. Watts means joules per second. Joule cancels off. As it goes up, it becomes seconds. You don't have to write units, right? I'm including the units because I need to clarify things. Okay, so 48. As it goes to the numerator, this becomes 2 over 3. 16 times 2, that is 32. So in order to provide 48 kilojoules with this power source, 1.5 kilowatt, you need 32 seconds. So these are, you just have to substitute in the equations, right? That's all you have to do. Okay, right, take it down. Right, so now I think you are familiar with that basic equation, work divided by time, right? The third essay question. Third essay question, if you want, you can draw a sketch. A whale with mass 8,000 kilograms, so that is 8 tons, gains a speed 12 meters per second. So initially he's at rest, then he gains a speed 12 meters per second within 6 seconds. Calculate the kinetic energy gained by the whale. So the initial kinetic energy is 0, then he gains a kinetic energy. So kinetic energy gained should be half mv squared minus 0. Initial kinetic energy is 0. This is final kinetic energy. Half mass is 8,000. V is 12 squared. So 4,000. 12 squared is what? 144 times 4. There are 3 zeros here. So 4 times 16, 17, 5. 576, 10 to the power 3, I'll write it as kilo. So this is the kinetic energy gained by the whale. 576 kilojoules, right? You can take it down. Then at the second part, if the resistive force on whale can be neglected, find the power required by the whale for this. Okay. So in order to gain this kinetic energy, something has to provide energy. Actually, whale itself with its fins gains this kinetic energy, right? So what is power now? This is the gained energy, which is equal to the work done by the whale. So you can say this is the gained kinetic energy or divided by time. So the time is 6. This is the gained energy divided by time. Okay. So divide by 2, divide by 3. So it is 96 watts. Okay. So this is the power of the whale. Actually, this power is provided by the whale itself. So it is 96 watts. Okay. So here we used energy gain divided by time. Okay. Because energy gained is equal to the work done. So always whenever you do work, that work always converts into a type of energy. So the work done is equal to that type of energy. So you can use that here, then divide by time in order to get the power, right? So it is 96, there's kilo, right? 96 kilowatts actually. 96 kilowatts. Take it down. Okay, then try fourth question. I'll give you a minute to try that. So you have 400 kilograms and it is lifted by a crane at 2 meters per second at this constant speed by a crane, right? So what they ask is power provided by the crane. Okay. So when you get a question like this, so if you need to move this at this constant speed, because this is 4000 Newton downwards, you need to apply a 4000 Newton upwards. Okay. So this is the driving force. Now we are going to use the another form of power equations. Okay. So that is P equals Fe. You can directly use this equation, right? This is a standard equation. So force applied, that is driving force, is 4000. Velocity is 2. So you can find 8,000 watts. 8,000 watts. Okay. So the answer should be a fourth one for that question. That is 8,000 watts. So whenever you have a force and a velocity. Consider using this one, P equals FV. P equals FV, right? This force should be driving force, right? This force is always driving force. That is what drives, what provides kinetic energy, right? Then times the velocity. So if you have any problems, use the chat box, right? If you have any problems, use the chat box. Right, then let's try a fifth question. First read the question and try that. Give you a minute. Try that first. So it is always better to draw a sketch, right? So let's say this is the cyclist. He is moving at constant speed, 5 meters per second. And the resistive force as he is moving, this could be air resistance to the cyclist, right? So the resistive force is actually, they say, 20 Newton. What they ask is power of the cycle. Usually that power is provided by the man riding the cycle, right? So the resistive force is 20 Newton. In order for the bicycle to move at this constant speed, 5 meters per second, it is obvious that the cyclist also has to provide a 20 Newton. So he's not, in order to cancel this force, otherwise he won't be moving at this speed. So in order to maintain this speed, he needs a driving force of 20 Newton. So this is driving force. Okay, now you have the driving force and the speed. You can simply use this equation. Force is 20, velocity is 5. So it is, so 100 watts is the power of the bicycle. So the answer is fourth one, right? Yeah, correct. Yeah. Answer is fourth one. Right, then try sixth question. First draw is sketch, okay? First draw is sketch. Try the sixth question. So when a boat with mass 150 kilograms is moving at constant speed 30 meters per second, power of the engine is 6 kilowatt. So this is the what provides the driving force, right? If the resistive force by water is constant, so there's a resistive force as it moves, there's a resistive force, let's say capital R, and there's a driving force as well, right? Otherwise it cannot have this constant speed. Let's say driving force is P. Distance that the boat moves after the engine is switched off. Okay. So from this one, this is the first scenario. At the first scenario, the boat is moving at 30 meters per second. Okay. So from this one, you can actually find this driving force. Just apply this equation. So the power is 6 kilowatt. Kilo means 6,000. F, here it is P, right? Driving force, I took it as P, times velocity. Velocity is 30. This is 30. So from this equation, you can find the driving force. That is 200 Newton. So this has a 200 Newton driving force. Okay, we found the driving force. Now we know this is moving at constant speed, right? If it is moving at constant speed, resistive force also should be 200 Newton. Correct? Or else you can apply F equals ma to this side. So P, it is 200 minus R. R to the opposite side is equal to 0. Acceleration is 0. We moving at constant speed. So now the resistive force, we found that as 200 Newton. Resistive force is 200 Newton. So this is the first scenario. The boat is still moving at constant speed. Okay. Then what happens? The engine is switched off. Engine is switched off means this P driving force gets removed. Now it only has a resistive force of 200 Newton at this moment. They say that resistive force remains at constant. And it has a velocity 30 meters per second. So the question what they ask is, after the engine is switched off, you know this already has a velocity, right? So this resistive force is working in order to stop this one. Now, since the engine is turned off, let's say it moves a distance s and it stops somewhere here, the boat, right? Here you can use, if you want, you can use F equals ma and motion equations. Easiest way is just use energy equations, right? You can use energy equations here. So how can we use the energy equations? If you notice here, the boat has a kinetic energy. Here the kinetic energy is 0. Kinetic energy is gone, right? That kinetic energy is actually consumed by this resistive force. So the work done by this resistive force should be equal to the kinetic energy the boat had. You can use this equation. Kinetic energy boat had is equal to work done by resistive force. Okay. We did similar questions at the last session. Okay. Right. Half. Mass is 150. Speed is 30 squared. Force is resistive force actually 200 times distance. Then you just have to simplify this. Let's see. 75. So this is 900 divided by 200 is equal to S. 0 cancels off. 75 times 9. 45. 63. 67. 675 divided by 2. 3375 meters. So when the engine is switched off, the boat can travel another 337.5 meters. Okay. So this is a good question, right? So you have to try this again, or you can rewatch this. Okay. Then once the engine is, even though the engine is turned off, this boat would travel this much of a distance. Then it would stop. Okay. So the answer should be fourth one. You can take it down. Okay, so you need to understand this 100%, right? Sometimes there are parts you might not understand. I mean, 100% you won't understand. But after a while, you can try that again. You can mark those theories or questions. Then you can try them again at a later time, right? Then when you try like that, it will make sense, right? So that is the practice you need to have, right? Then try a third MCQ. Try the third MCQ. You can draw a sketch. Right, within the time that an old car initially at rest. So there's this old car at rest gains a speed v. Then you have a new car. It also accelerates, but it gains a speed 2v. power ratio between old car and new car is? Old car and new car is. So that's what they ask. So how do we find this? They say that the mass, same mass, right? Both cars have the same mass. So this is the first scenario. Then you have the second scenario, that is new car. So what is power? You can use energy gain divided by time. So that is power. Work done is equal to energy gain. So here the only energy gained is kinetic energy, right? So this gain, initial kinetic energy is 0. This gains the kinetic energy half mv squared. So this is old car. Then the new car, it gains the kinetic energy same mass, velocity is twice, 2v squared. So does it happen at the same time or something? Yeah, it happens at the same time, right? You need to divide by time. So then you just have to divide these two in order to find the ratio. So it is obvious that half m cancels off and t cancels off, v cancels off, but there's a 4 here. That is the only thing that remains. So this is the ratio. So it is 1:4, PO to P nu. Okay. The speed is doubled at the second case, but power is 4 times, right? Because that speed got squared. Got it? That speed got squared. So some students would think, can you use P equals FV here? Here. You cannot, right? Why? This force, you don't know the force. If you want, you can find this force using F equals ma, but you don't know the force here. Driving force, you don't know, right? You can find this. That is the another way to do that. You can find this and substitute it here, but you don't know at this moment, right? So if you need to know the driving force, at the previous question we knew the driving force, right? Because we could find the driving force there. So here it is better to use this equation, energy gain divided by time. If you want to use this equation, you will get the same answer. But if you are going to do that, just apply F equals ma and find the acceleration, then find the driving force. Then you can substitute those driving forces here and here for these moments, and you can find the power in that way as well. But this method is better here because it is simple now. Okay. So the answer should be third one for that question. Yeah, correct. Correct. Third, right? Right. We'll try first turn. We'll get it done, right? First turn. Just read the question. Consider the units below. So what they ask is a unit of power. Okay. So for the option A, we have kilowatt hours. Just because there's watt here, it doesn't mean that is a unit of power. This is actually a unit of energy, right? Energy. Let's say why that is. So kilo means 10 to the power 3. Watt means 1 joules per second. Hour means 3600 seconds. So second per second cancels off. Then what do you get? 3600 10 to the power 3. Look at the unit. When you simplify the unit, it becomes joules, right? So this is a unit of energy. Kilowatt hours is a unit of energy. So the electric bill in your homes has this one, right? You are charged for the amount of electric energy, that is kilowatts hours. kilowatt hours. You are not charged for rate of power. You can't be charged for rate of power. You are charged for the energy, right? Not the rate of energy. So it is measured, electricity, that is energy, that is usually measured using kilowatt hours, okay, usually. Then let's move on to the second unit, that is electron volt. You might not familiar with this one, but when you're doing last lessons in the syllabus, you will like matter and radiation. Many times you will see this unit, electron volt. I'll just explain this. Electron means, E means charge of an electron. So it is roughly this much coulombs, right? Charge is measured in coulombs. What you have here is volts. So volts means, you will learn this at electric fields. 1 volt is equal to 1 joules per coulomb. Then coulomb cancels off. What do you get? 1.6 10 to the power minus 19 joules. So this unit is useful when you are doing questions regarding atoms, right? Regarding energy levels of electrons, things like that. You oftentimes you have to use electron volts. Okay, so it is obvious that these two are not used to measure power but energy. Then the another unit, that is joules per second. So joule divided by time. So this is the only unit that can be used to measure the power. So the answer should be third one, right? Only C. Take it down. Okay, then try a second question. I'll give you a minute. Try second question. So power consumption of a country is 40 gigawatts. So what is giga? So that is a prefix, right? Giga means 10 to the power 9. So 40 10 to the power 9 watts. This is the power consumption of a country. Okay. So per second it consumes this much energy, right? So because this is a country, okay. Then they say by burning 1 kilogram of coal, 1 kilogram of coal, it provides 20 megajoules. Mega means 10 to the power 6. Just convert everything into just joules, right? It is easy. Then they ask if the energy requirement is completely gained by burning coal, rate of burning coal should be. Okay. Right. Let's see how to do this. So the power requirement is this much. This much. So when you get a question like this, you can think about units, and the final unit should be kilograms per second, right? So that is at every second this many kilograms should be burned of coal in order to generate this power. Let's say per second you need to burn this much. Let's say m over t. So this is the mass rate. Per second this many kilograms is burned, and that kilogram, 1 kilogram has this much of a energy. Then you have to multiply that here. When you write something like this, always you can check the units in order to get that, right? So what you need is m over t. Per second this many kilograms. So per kilogram this much energy is released. So per kilogram this much energy in joules, then multiply that by the mass rate, then you can get the power there. Correct? Then you just have to substitute values. So the power is 40 times 10 to the power 9. So m over t is what you need to find. 20 times 10 to the power 6. 6, this becomes 3. 20, this becomes 2. So m over t is equal to 2 times 10 to the power 3. Since this is a mass ratio, it should be kilograms per second. In order to gain this amount of a power, 40 gigawatts, you need to burn, this is 2 tons, right? Per second, you need to burn 2 tons of coal. According to the data given, you need to get 2 tons of coals, right? Here you might be wondering what this equation is, right? You can think about units and get an equation like this. Okay, right. So the answer should be third one, 2 times 10 to the power 3. Here you can think about units, right? Kilograms per second. What is this? This has joules per kilogram. If it is hard to think, you can think in terms of units. This many joules is produced per kilogram. So the unit of this should be joules per kilogram. Unit of this one is kilograms per second. Then kilogram cancels off. What you get? Joules per second, which is watts. Okay. Finally, this whole thing is reduced to watts. Joules per second. Ready? Joules per second. Meaning that should be equal to the power. Okay. If it is too hard to think about that, think in terms of units. So you would get the final answer correctly. Right. So the answer is third one for the second question. I have discussed all the types of questions you might get from the power. Then we'll move on to efficiency. Write down the subtopic efficiency. Efficiency. So what is efficiency? Efficiency. So efficiency and power, there are two different things, right? Completely different. So you know, when you have like, let's say this is a system, or we can consider this to be like a machine. So if you provide energy to that, you get an output from this. This input can be work, energy, or in terms of power. So the output also you gain it as work, some type of energy, or power, right? So you provide some energy or work into the machine, so then you get output, desired output from the machine, something useful, right? So this machine can be considered like a, let's say, electric bulb. So what do you provide to electric bulb? You provide electric energy, electric current. That's what you provide, electric bulb. Then what do you get as the output? As the output you get light. Here the output is only the useful output, right? We don't use electric bulb to generate heat. We need electric bulb to generate light. So light is the output. So this output has to be useful. This has to be useful. Here you have the supply. Total that is what you supply. You have to supply some energy for the bulb. In terms of a bulb, it is a electric energy. Then you get light from the bulb. That is useful. So the ratio between these two is what we call efficiency, right? That's what we call efficiency. I'll use another equation. I mean another scenario. For an example, let's say you have a heater, right? Electric heater. So using electric heater, what you need is you need heat, right? You only need heat. So when you provide electric energy, output is just heat. Okay, so that is a very efficient apparatus, electric heater, because electric heater, we are not using electric heater to get light. You use that to get heat, right? Right. Like that, there can be many types of examples. So those are the easiest examples that I can explain, right? So the equation for efficiency, this is the unit we call this eta, efficiency. So it is equal to output divided by input times 100%. This is the equation for efficiency. Or sometimes they say it is the same equation. In some questions, you will need this one, useful divided by supplied times 100%. Useful divided by supply energy times 100%. So that also can be efficiency there, right? So usually we express efficiency in terms as a percentage. That's why you need to multiply by 100% there. We'll see when we are doing questions, right? Just take everything down, and if you have any problems, send me in the chat box. Right. In order to further clarify this, we'll try some of the questions. Try 7th MCQ. 7th MCQ. Right. So efficiency of a motor with power 800 watt. So this motor has a 800 watt and the efficiency is 60%. What does it mean? So what they ask is waste of power of the motor. This 60% means when you have a motor 800 watts, meaning of that is you need to provide the motor 800 watt, right? 800 watt. You need to provide 800 watt to the motor as electric energy. Then only 60% of that, this is the efficiency. Only 60% of that is generated as mechanical energy. So we use a motor in order to rotate this stuff, right? In order to rotate this stuff. So from 800 watts, only 60%. 60% means 60 divided by 100. This cancels off 8 times 6, 48, 0. So this is the output. That is 480 watts. Okay, this is the output. So you provide 800 watt, but the output is only 480. So what is the wastage? So the waste power is 800 minus 480. 0, 2, 7 minus 4, that is 3. 320 watts. Right? So this is the waste. So this 320 can be as heat. Mostly this 320 is heat. So besides the mechanical energy, motor produces heat, right? So that's it about efficiency. Okay, so I'll explain again. So you provide 800 watt as electric power to the motor. Only 60% of that is converted to mechanical energy. That is the useful power. So the remaining amount, so that is 320, is a waste. It is wasted to the surrounding as heat, right? So the answer should be second one there. Got it? Answer should be second one. Take it down. And if you have problems, send me in the chat box. Then try fifth essay question, right? Fifth essay one. Draw a sketch first. Draw a sketch. So a man lifts a stone 20 kilogram to a height 0.2 meters. Let's say this much. So in order to do this, he uses a lever. Levers, you have heard in O levels, right? Levers. It can be a pulley system. It can be like a seesaw, right? So we'll think about a simple, let's say this is the lever. So the man is applying a force from this side. So when the man lowers this, this end goes up to 0.2. But in order to do that, he has to move this lever 1 meter distance by applying a force 60 Newton. So this is man. This is the supplied work or supplied energy. As a result of that, here the machine is the lever. So the output work is this 20 kilogram is lifting up to 0.2 meters. So if the man directly, without the lever, if he needed to lift this, he needed 200 Newton force, right? At least a 200 Newton force requires. But using the lever, he only needs 60 Newton. Only needs 60 Newton. Okay. In the first part, they ask find the increase of potential energy of the stone. So so for the first part, it is just mgh. So the mass is 20, g is 10, h is 0.2. 2 times, so it is 40 joules. This is the increase of potential energy. This is actually the output. Understood? This is what we need to do, right? So that is the output of this machine. Then work done by the man. So the work done by the man. So the force applied is 60. He moves this 60 Newton 1 meter. So he is doing a 60 joule of work on this lever. Right? Can you understand? This is the input. Correct? This is the input. Man provides the input. And that is the output. Final result of that, the useful work, is the stone moving from here to here. So that is what we need to do, right? Then at the third part, they ask efficiency of the lever. So what is the efficiency? Let's say eta. Eta is output divided by input times 100%. So the output is this one, right? 40 joule. Input is 60 times 100%. You need to provide that as a percentage. That's why we multiply by 100%. This cancels off 2, 3. So this is 200 divided by 3%. I multiply by 100, right? So percent is remaining here. So 20 divided by 3, that is 6. 2 is remaining, 6.7%. So this is 66.7%. That is the efficiency of this lever. So in this lever, we don't have perfect machines, right? Even this only converts only 66.7 as the useful work from the input work, right? The remaining amount, about 30% something, is wasted. There can be friction, those stuff, so it can generate heat and all those stuff, right? So that is about 30% something has been actually 33%, right? 32%. something is removed, wasted energy there, because this only has a 66.7 efficiency, this lever, right? Take it down, and if you have any problems, please send me in the chat box, right? Right, then we'll try a sixth question. While a machine does useful work of 50 joule, energy wastage is 30 joules. Find the efficiency of the machine, right? So let's say this is the machine. So the machine, they say the machine does a 50 joule of useful work, right? This is not input, this is the output, because useful work. And the energy wastage, they say that is 30 joule. This is wasted amount, wasted energy amount. So this is a useful amount, this is the wasted amount. Then sum of these two should be the input, right? So always input energy, part of wasted and part converts to the useful energy. So the input should be 80 joule. That's what we have to understand. When you provide 80 joule, 30 wasted, 50 is converted into useful energy. Then what they ask, efficiency. So the efficiency is, I'll use this equation, useful divided by supplied. So the useful amount is 50. Supplied amount is what? 80. That is what they give you the question in different words, right? But you need to understand the idea and find what is the input, what is the output. So this is useful, that is output. This is the input. 80, 100%. So this is 500 divided by 8%. So 4, 250. 250 divided by 4, that is 6, 2.5%. So the efficiency of the machine is 62.5%. Got it? Take it down, and you have to redo these questions, right? Right. Then try 8th question. Draw a sketch. So 8th question, a pump with efficiency 50%. 50%. Lifts mass of water 7,200 kilogram. So let's say this is mass of water, this amount of mass, right? And it is lifted to a height 100 meter. So this is the useful work, right? So the motor is used to lift water to a 100 meter height. What they ask is input power of the motor. Input. They ask the input, right? Not output. So this is actually the useful work. This is the output we need from the motor. In order to gain that output, we have to provide an input, usually as electric current, right? Electric energy. Let's calculate this one. The energy here. So mgh. Mass is 7,200. G is 10, H is 100. So this is 7.2, 10 to the power 3, 10 to the power 3, 10 to the power 6 joules. So this is the output. This is the output or the useful work, right? Useful work. And this is the equation. Output divided by input times 100% is the efficiency. So what they ask is input, right? So I can cross multiply this. Input is equal to output divided by eta times 100%. Okay, so the output is what? This much. 10 to the power 6 divided by 100%. Sorry, eta. If you want, you can neglect this 100%. What does 100% mean? 100% mean 100 divided by 100, right? So this is 1. If you want, you can multiply. You don't have to multiply. Doesn't make a difference in the question. So eta means efficiency. This is 50% is the efficiency. What is 50%? That is 50 divided by 100, right? So 50 divided by 100 is 0.5. So 0.5 is 1 over 2. That is half. When half goes up, it becomes 2. 2 times 7.2 is 14.4 times 10 to the power 6 joules. So this is the input. This is the input. So when you provide this input, you gain a 50% of that in order to lift this amount of water from to 100 meter height. So do we have an answer for that? So they asked the answer in watts, right? Not joules. So in order to make this watts, you have to, so the whole thing is done within an hour, right? So I found this, it is better if you initially divide it by that time, 1 hour. 1 hour means 3600 seconds, right? It's fine. Now since we have done the question, at this stage also you can divide it by 3600 seconds. So this is 0.36, this is 0.4. 0.4 4 times 10 to the power 3 watts. In watts, this is the amount, right? So this is 4 kilowatt. This is 4 kilowatts. That is the input. So when you provide a 4 kilowatt of input, if you want, output also can be written as in terms of power. You just have to divide it by 3600 for 2. So this is 2 kilowatts. You get a, when you provide 4 kilowatts, you get 2 kilowatts of power. Right? 50%. See that? Another 2 kilowatt is wasted through the motor. Right? When you provide 4 kilowatts, 2 kilowatts convert into the useful power. Another 2 kilowatt is wasted, right? In almost all the machines, there's always a waste. There's no machine that can provide 100% efficiency, right? Practically any machine, you can assume a theoretical one, but practically any machine always, the efficiency of it is less than 100%, right? So the answer is third one for the 8th question. Take it down. Right, then we'll try 9th question. 9th question. Give you a minute, try that. Right, so we have a 1 kilowatt pump. 1 kilowatt pump means, so you have seen in motors or in electric bulbs as well, they have printed this watts amount, right? That watt amount is not the supplied or the useful work, power, it is actually the power required by the machine, right? Power required by the motor, that is 1 kilowatt. So you have to provide 1 kilowatt as electric power to this one. So 1 kilowatt is the supplied. So what does the motor do? It lifts 300 kilograms of mass to a height 10 meter, then ejects at 5 meters per second, right? So all this is done within a minute. Minute means 60 seconds. So this whole process is the output. So you need to find output power. How do you find that? Power. So energy here, mgh plus, it is given a kinetic energy as well. Then you need to divide it by time. So mgh, mass is 300, g is 10, h is 10, plus half, mass is 300, velocity given is 5. Then divide the whole thing by 60. So with all this is done within 1 minute, right? I'll just divide by 60 both. So here you get 5, here also you get 5. So this is 500 plus, this is 25 times 5, that is 125, divided by 2, 62.5. What do you get? 562.5 watts. What is this? This is the output. This is the useful power. So the input is 1 kilowatt, that is 1000 watts. Output is 562.5 watts. So what they ask is efficiency of this motor. So output divided by input, 100%. Output is this much. Input is 1000. Multiply by 100%. Right? 2 zeros cancels off. Then divide by 10. 56.25%. Right? So this is the efficiency of the motor. Okay. These are like really important questions, right? I suggest you do these questions again, and if you have any problems, you can send me the problems, right? So that is the 9th question. So since we are running out of the time, I suggest you do the last question, that is 7th question at home, right? 7th, that is also a good question. And if you have any problems with that, please send me, please let me know, right? Try this 7th question at home, okay? Then you have to redo these questions if you need to get the expertise in these parts, correct? Right. So in the next class, there's a new phase. Now we have covered all the fundamentals, right? All the fundamentals in mechanics is we have covered. Then we are going to do rotational motion at the next classes. Rotational motion, circular motion, hydrostatics and hydrodynamics. Right? Hydrodynamics. So you need to get ready for these. And if you have any problems from the parts we have discussed so far, please let me know. Okay? Right. Then good night, everyone. Right? Good night, everyone.